Okay, welcome everyone to our seminar. Our speaker today is Guillermo Cortiñas, and he will speak about K-theory and homology of Steinberg groupoid algebras.
Thank you very much. So everything I know that I'm going to say today is joint work with Guido Arnone and the Varsi Montelji. So throughout the talk, G will be an output groupoid. So this is, it's a tal, and Z0 is Hausdorff, which I will abbreviate as usual T2. Is T2 and has the basis of compact opens. Okay, now K will be a commutative ring, unitary ring. And I will write AG for the K Steinberg algebra on D. Okay. Now, I'm interested in the homology of this algebra and the homology of the groupoid. So the homology of the groupoid with coefficients in K is defined by a complex which, as far as I know, was introduced by Kreinich and Merdijk. And well, there is a complex, you take this homology, and this can be interpreted as Tor groups over the Steinberg algebra of the Steinberg algebra of the units. So the Steinberg algebra of the units is a module over AG, and you take the Tor groups, and that is group of homology. This was established in a paper by Xin Li. Okay, so that's one homology we are interested in. Another homology which is defined for any K algebra R is the Hochschild homology. So this is defined as Tor groups over this ring. So R op is the opposite ring. Both R and R op are K algebras, and I take the tensor product. A module over this is an RE module. So it's a bimodule where the action of K is symmetric. It's the same on both sides. So for such this is the enveloping algebra. I will assume that this is flat. That the R is flat, as is the case of the Steinberg algebra. And then the Hochschild homology of the algebra with coefficients in the bimodule is given by the Tor groups over the enveloping algebra of R and F. And when M coincides with R, then we simply write HH of R. Okay, so now I'm going to state a general result about the Hochschild homology of Steinberg algebras. And I need a piece of notation for x in Z0 that is defined the isotropy group consisting of the G's whose domain and codomain agree with X, Ri, D, and C for what is usually called S and R, because I have another use that will be uncovered later on for R and S. Okay, so this is a isotropy group of G at X, and the isotropy is the union over all X in J0 of GXX. This contains Z0. Since G is a tanh, Z0 is open in G, and in particular, it's open in this with the subspace topology. And this is as a subspace of G, it also has its topology. Okay, so we have the following theorem. Suppose that G is Hausdorff. Then, first thing is that the Hochschild homology of AG contains the groupoid homology of G with efficiency in K as a direct sum. So we identify, so we show that the standard Hochschild homology complex for an algebra R is quasi-isomorphic in a case of a groupoid algebra is quasi-isomorphic to a certain complex which contains the complex, the Greenwich-Mellon complex as a direct sum. So that's how we establish this. Now, what can we say about the question mark there? Well, first, if G iso coincides with G0, in which case G is principal, then groupoid homology is the whole of Hochschild homology. There's nothing else. And the other case in which we can say something about the question mark is when G iso minus G0, which is so it's a closed subset in G iso, when this happens to be discrete. In this case, this question mark is a sum. I will explain what my notation is in a moment. What is important here is that I get this described as a direct sum of group homology of certain groups. I will explain my indexing. So first of all, what is R? G acts on G0, right, by conjugations. And one takes a set of representatives for this action inside of G0. And that's, so I take 1x for each one. So I take the sum over all representatives. And for each representative, I look, for each x, I look at the conjugacy classes of GXX, for the isotropy of x. And G psi is a choice. I make a choice. I take a representative of the conjugacy class. And then I look at CG, the centralizer, inside of GXX. So again, this decomposition is as the sum of the homologies of the centralizers of representatives of conjugacy classes of all the GXXs. Okay. Here I should remark that in the groupoid case. So when I write Roman G, I mean a group. When I write this cal G, I mean a groupoid. So when a groupoid is a group, this decomposition was due to Borgiglia, and it's in a paper he published in 1995, which is 40 years ago, so we can now consider it a classic. Okay. So we recover Borgiglia's decomposition in the group case. Okay. And then I have several other remarks to make. So, well, Cauchy homology is related to other bunch of homologies, such as cyclic homology, negative cyclic homology, and periodic cyclic homology. And yeah, our result also covers this. So so the chain complex, the standard chain complex for Cauchy homology has the structure of a cyclic module. And thus, if it gives rise to three other complexes, cyclic homology, negative cyclic homology, and periodic cyclic homology. Okay. And on the other hand, this guy is also a cyclic module and has a cyclic homology, which I will call HC of G, Hn of G, and HP of G. And I don't write it to say to avoid clutter, but all of this depends on K. Well, each of these is a direct summand of the corresponding complex for when R is the Steinberg algebra, is a direct summand of the corresponding cyclic, negative cyclic, and periodic cyclic homology. And moreover, we can describe the homology of each of these in terms of groupoid homology. So, for example, Hn of G at level n is the product over P bigger or equal than 0 of Hn plus 2P of G K. Okay. And if in the case of HP, you get a similar product, but over all integers P, not necessarily positive. And for HC, you get P positive, but instead of a plus here, you get a minus. Okay, so we have this decomposition for all the homologies, but I point out negative cyclic homology because, as I said, this for R equal A of G, this is a direct summand in the negative cyclic homology of R. And well, you can map K theory of a ring of a K algebra to its negative cyclic homology, and this is called the Chan character. Negative cyclic homology naturally maps to Hochschild homology by a map called S, as in the SVI sequence. And this composition is the Dennis trace. So Dennis defined this trace to Cauchy homology, discrete map, and Goodwillie showed that the Dennis space lifts to a map going to negative tricky homology. Now, in the Steinberg algebra case, this contains Hn of Gk as a direct sum. And you can project onto here. This is the projection onto the first factor, and this diagram commutes. And then you have a map from case theory to the product of the groupoid homology groups, and also to the single groupoid homology. And this is interesting, so I will call the composite will be CH bar, and the other composite, the D composite will be D bar. Why is this interesting? Well, because of Mathui's HK conjectures, which predicts a relation between the homology of between the case theory of the reduced sister algebra of a groupoid and groupoid homology. So let me state this. So who is HK projection? Sister algebra T is isomorphic to the sum. To the sum over P greater or equal than 0. Let me see here. P is 2 over the of Hn plus 2p of G with coefficient in Z. Okay. So this is not the sister algebra, but the Steinberg algebra. But it's interesting to point out that there is a natural map from the K-theory of the Steinberg algebra to something similar. We have a product here instead of the sum, but say the group of homology vanishes about a certain degree, then they are the same. Right, so that's one motivation to study this map. Actually, we'll find that the D bar already contains quite a lot of information, which is what we will study in particular. Right. But we want not only to consider Steinberg algebras of groupoids, but also twisted Steinberg algebras. So by a twist, so there's a more general definition of twist, but the one we will consider is that given by a two-core cycle with values in the units of K. Okay, and so so we have the groupoid together with the two-core cycle. I will denote by G sub omega being the two-core cycle. Right. And then I want to map K-theory to twisted homology. With a homology of this twisted groupoid, we have a definition which I will not give you, but just let me mention that we define a certain complex of twisted homology, and we do it relative to a subring L of K. I will explain why. So that this is naturally split direct summand of the Hochschild homology of AG relative to L. So what is all this relative business? I mean, if you have an algebra over a ring R over a ring K, and K is itself an algebra over another ring L, then your original K algebra becomes naturally an L algebra, right? And then you can take, even if the algebra of the groupoid algebra is taken with coefficients in K, you can take its Hochschild homology over some subring A. Now, why would you want to do that? Well, this cocycle takes values in K. And the homology of K over itself is trivial. So, if you just take homology relative to K and not to a smaller subring, then the difference between having the cocycle and not having the cocycle will be lost in homology. And we don't want that, so we consider this relative to a flat extension. If you want to keep an example in mind, perhaps you can take K to be the complex numbers and L to be the rational numbers. And if, say, your W takes values that are transcendental numbers, then they will give you non-trivial classes in Hochschild and in cyclic homology. So, yeah, this is why we do this. Okay, and so we have for G2, we have a reduced dense trace for Kn of AK of G twisted by W to this homology N of GW relative to this extension. And this is what we want to start in concrete examples. And the concrete examples, we study them in is that of Exel-Pardo groups. Okay. So let me remind you the setup of Exel-Pardo groups. So we start with an oriented graph. Right. I guess you can see very well because this is a still way. Let's see. You see this E. E1 is the set of edges, and E0 is the set of vertices, and the maps are called R and S, the range and the source. So an edge E is viewed as a little arrow that departs from its source and lands in its range. Okay. Today, we will assume that E is row finite, which means that for every B, for every vertex B, the number of edges in the mix that is the pre-image of the source map at B is always finite. And since we are talking about the vertices that the edges that depart from a given edge, let me introduce one piece of notation that we will need later. These are range E consists of the vertices such that this number is not only finite, but also positive. Right? So my E is assumed to be row finite, and then a vertex in a row finite graph is called regular if it emits at least one edge. Right. Okay, so we have the graph, and now we have a group G acting on E1, just on the edges. And we want that if G goes from B to W, then not G, E. If E goes from B to W, then GE will also go from B to W. Okay. One can consider more general actions, as Exel-Pardo do, where G also moves the vertices, but we will restrict our attention to those that where those actions where the action on the vertices is trivial. Right. So suppose you have all this, and furthermore, one more piece of data. We have a map from G times C1 to G that satisfies the following cocycle condition. Say you want to evaluate phi at the product of G and H, comma E, the vertex E, then this will be equal to phi of G evaluated at H times phi of H. Okay. With all this data, you can extend the action of the cocycle and the action of G to arbitrary to paths in E of arbitrary length. So recall what the path is. The path is equal to C1 En such that the range of EI is the source of EI plus 1 with every I. And so here I have my phi defined on pairs GE. So when E is a path of length 1, that is an edge. And say I have already defined phi of G at alpha, and I add one other edge, right? So this is defined as phi of phi GE. This is an element of G, G alpha, sorry, evaluated at E. Okay, so this recursive definition that defines you phi of G alpha for alpha a path of any length. And now you want to define by the same recursive idea, you want to define what G evaluated at alpha E is. Well, this is G of alpha times phi of G alpha evaluated at E. Okay. Now that we have all this, we can consider the Exel-Pardo semigroup. This is an inverse semigroup. Its elements are of the form alpha G beta star, where G is in G, and alpha and beta are paths that end in the same vertex, union 0. So how do you multiply to all these guys? Well, the beta stars and the alphas multiply as in the Levitt path algebra case. If you are familiar with Levitt path algebra, you know what I mean, and if not, well, it's very long to explain. But let me tell you how I multiply So here I have an alpha and then a G and then a beta star. So what happens if I want to do G times alpha? Well, G times alpha is G of alpha times phi of G alpha. And what about beta star times G? Well, this is phi of G inverse beta times G inverse beta star. Okay? So this gives you a product. So if the product, I don't know what to do, what this don't match, then it's zero. Okay? That's what the zero is for. So you get an inverse semigroup, and an inverse semigroup has associated the so-called universal tight groupoid. In the sense introduced by Excel, by Ruby Excel. And yeah, this is the groupoid. This is the Exel-Pardo groupoid of the field G in phi. Okay, but not happy with how complicated the Exel-Pardo groupoid is, we want a twist of it. And to get a twist, we get a twist from the map C from G times C1 to K, to the units of K, that satisfies this same identity. So C of G H A at E is G of G at H of E times C of H E. So this using this C, one obtains a groupoid twist in the sense I said before. So a tuple cycle, and with the tuple cycle, one forms the twisted Exel-Pardo groupoid. So C gives rise to some tuple cycle to K star, and the twisted Exel-Pardo algebra notice I have the phi and the C. At the C, I put it as a subscript of phi to incorporate it into the notation. And then I call them L because to avoid all this stuff. And then what is this? This is the Steinberg algebra of this twisted groupoid. So who is G? This is G. Okay, now if you by a result of Steinberg says that when you have a groupoid that comes from a semigroup or an inverse semigroup, then you have a surjection from the semigroup algebra to the Steinberg algebra. And here, this also holds when you have a twist, and here you also have a twist induced by C. So, never mind, but what I want to mention this is to say that the Levitt-Path algebra, the Exel-Pardo algebra, is generated by the elements of the groupoid. So each element of the semigroup, each element of the semigroup gives an algebra element, and the map is surjective. Okay, and so L gets a Z grading where the degree of alpha G beta star is the length of alpha minus the length of beta. Okay, so this gives you the Z grading, and when you have a Z graded algebra, the Hochschild complex decomposes into a sum, a direct sum of complexes, one corresponding to each degree. This is the so-called weight decomposition. Okay. So without further ado, I can now go to say what the results about Hochschild homology are in the Exel-Pardo groupoid case. So I will, for brevity, for reasons of brevity, I will describe the first part of this just vaguely, okay? So, right. So for every M in Z, we get a long exact sequence that relates HHM of L related to computed over this all the subring L of our ring of coefficients K to the Hochschild homology of Kg relative to L with coefficients in a certain bimodule on a certain G bimodule Sn. So we get such a long exact sequence, and I will tell you what the sequence is when M is 0. So when M is 0, we get HHN of K of G relative to L as many copies as there are regular vertices in it, then sum up, then I go to HHN of K of G relative to L, as many copies as there are vertices in total, and then HHN 0 of L relative to L. And you can imagine how it goes. So why I zero on the 0th weight? Because because this contains the groupoid. This is where the groupoid, the group homology lives. So the group homology is a direct summand in here. The group same in here. And same in here, but here I need to assume, and this is the twist, that so this is, so we show that the Hochschild homology of the Steinberg algebra contains the twisted groupoid homology when G is Hausdorff. Right. So you may guess that perhaps at least in the Hausdorff case, you have an exact sequence here that is a direct summand of the sequence above. We were able to establish this, but we need further assumptions. So up to here, we need no assumption. Now, for this, we need that G, E, phi be pseudo free. So this means that for every, so if you have a G such that and an alpha such that G alpha is alpha and phi of G alpha is 1, then G must be 1. So if G, so this alone means that G fixes the path alpha. Adding this, it fixes it strongly because this means that no matter how you continue alpha, it will always be fixed. Okay, so such an alpha is fixed by G, and any continuation of alpha is also fixed by G. So that's what we call G, that G strongly fixes alpha. So the pseudo freeness means that cannot happen unless G is the trivial. This already implies Hausdorffness, but it's stronger than alpha. Under this hypothesis, we managed to establish this sequence as a direct summand of this sequence. Now, the sequence below, independent of Hochschild homology, is known under more general and the more general complete generality is a result of Miller-Steinberg that established a sequence like the one below, for general without this assumption, but they do not establish that this sequence matches as a direct summand of this, and they also consider the untwisted case. We consider the twisted case. Okay. So now you may ask, well, so we wanted to map K-theory to homology, to groupoid homology. So, well, we have a strong this hypothesis. We have the groupoid homology. So, what about the and how it sits inside of Hochschild? So we know we can now map K to HH and then to groupoid homology. And well, what about K theory? And how does it map to homology? Well, I have to mention some more vocabulary. So we have a ring R, and this is called Kn regular. If for every M, Kn maps the inclusion of R into the polynomials in M variables over there to an isomorphism. So the short way of saying this is that Kn of R is the same as Kn of the polynomials, but not only that, it's the canonical, the isomorphism is induced by this canonical map. And an old theorem of Bohr's says that Kn regularity implies Kn minus 1 regularity. Okay, and well, so we have homotopy algebraic K theory. So even if you don't know anything about K theory, you may guess that if we give a name to the rings such that Kn of R is the same as Kn of the polynomials, this must be because this doesn't hold in general. And in fact, that's correct. K theory is not homotopy invariant. This is Wheeler's K theory. Now, homotopy, and this is Weigel's homotopy algebraic K theory. Weigel's homotopy algebraic K theory is a version that is always homotopy invariant, and which receives a canonical map from Willens, and this is an isomorphism if R is K and regular. Okay? And so, for example, if K of G is K regular, so K regular means Kn regular for all n. If K of G is K regular and G E phi is pseudo free, then A of GW, AK of GW is K regular. Okay. So for the kind of rings where our we have the computation for groupoid homology and that it behaves well with respect to Hochschild. For those algebras are precisely, for those algebras we know that KH is the same as K. And so I mention all this because we compute KH. We complete generality, we compute KH of the twisted Exel-Pardo algebra. I mean, not completely. In the generality I mentioned today, that E is row finite and the G acts trivially on the vertices. So we have a long exact sequence that goes as follows: KH n of KG to the raised E goes to KH n KG, E0 goes to Kn of L, goes to Kn minus 1 of Kg to the edge. Okay. Yeah. And so in the case when Kg, when these conditions are met, so if Kg is K regular and G E5 is pseudo free, then we know that K is KH. Okay, and for in this case, we have established an analogous sequence of twisted groupoid homology, and this one maps to the other in the obvious way. So we have to determine what the maps are, and we do this in the following. We do this in low dimensions, and we need one further assumption. So we have a group G that is torsion free. Then the Farrell-Jones conjecture, the Farrell-Jones conjecture for the torsion free and K must be a field or a PID, a principal ideal domain. Then if G is torsion free, K is a field or a PID, and satisfies the Farrell-Jones conjecture, which predicts a certain description of algebraic theory with the group algebra, then Kg is K regular, and Kn of Kg is Z for n equals 0, K, the units of K plus G abelianized for n equal 1, and 0 for n more than 0. I'm not telling you what it is for n equal to 2 and above. Okay? Okay, so I will use this information. So under these assumptions plus the pseudo-finesse assumption, I can compare this K, this KH is K, and I can compare this case with the groupoid homology. And I will do that as soon as I like this. So first off, I need to tell you what the maps in the long exact sequence are in long dimension. And for that, I will introduce 3 matrices. So 4 matrices. One matrix is the matrix I. It lives in Z P0 times reg E. So it has as many rows as it has vertices and as many columns as it has regular vertices. And EBW is Kronecker delta BW, so it's 1 if B is W and 0 squared. So it's a truncation of the identity matrix, and if all vertices of E are regular, then it's exactly the identity. Then I will take a matrix A in Z, but the reg goes in the rows and E0 goes in the columns. And then I will transpose. But this is, I follow a custom, so I don't dare, disrespect. So A, BW is the number of edges E that go from B to W. And then for each G in G, I will consider a matrix B of G that lives in G to the reg E times C0. B of G in BW is a product over all edges C that go from B to W of phi of G E. And then another matrix C of G in K, in the units of K, reg E times C0. C of G in BW is the product, again, over all edges from B to W of C of G E. And this I have, and there is a sign that I can explain if some of that, but there is a sign. Okay, so then under the assumption that under these assumptions, I get an exact sequence as follows. So I get K star plus G up to the reg E goes to A star plus B up to the E0 goes to K1 of L, then goes to Z to the reg E, and then Z to E0, and then K0 of L, and then 0. And this map is I forgot to introduce D. So D of G is the matrix A, C of G, B of G. So it's a matrix of homomorphisms. It defines the homomorphism. If I transpose it, it defines the homomorphism from here to here. And here I get I minus AT. Okay. And so this is the law the sequence established above in low dimensions. And so we get that so for G torsion free for L Jones and K PID for a field, we get that K0 of L is just a cokernel of 1 minus AT. This is called the Bowen-Franks group of T. And 2, K1 of L appears in a short exact sequence, where here we have coker of I minus dt. And here we have care of I minus AT. Right? So, yeah. And what about the homology? Well, if we add to the hypothesis above that this be pseudo-free, we get that H0 of G KL is nothing but BFE tensor with K. And the map is a scalar extension, as you may expect. So, for example, if K is the integer, then you get an isomorphism between K0 and the zeros group with homology. And again, under this pseudo-freeness hypothesis, here I get a similar description of H1G K model, where here I get care of K tensor I mod 8 I minus 18. So the K is inside. You can, if K happens to be flat over the integers, then you can pull it outside. And here we get the cokernel of a matrix 1 minus MT. And so what is M? What is M? So M, so remember, this is K1 of the group algebra, this is K1 of the group algebra, this is K0 of the group algebra, this is K0 of the group algebra. Right? So similarly, with groupoid homology, we have, so what is the groupoid homology 1 of G K relative to L? Then this is the Keller 1 differential forms of K relative to L plus H1 plus H1 of G. So this is G up tensor with K. And if you have an element, any invertible element in K, you can consider the logarithmic, the d log of the unit, which gives you an element in K. So M is the matrix which has A here, B here, and here is B here, and here it has d log of C. Notice that, so if K is L, this is d log, right? So that's where I was getting at when I said that we needed to take precedence in some smaller ring L. And yeah, and then this is the matrix that appears here. Okay? So to finish, let me give you a concrete example. So suppose that W is trivial and that K is flat over the integers. Then we get an exact sequence as follows. Okay. So let me see, let me explain this. So here is K1 of L, no L, you tensor it with K. So if K happens to be Z, then you may disregard this. Then these maps are onto groupoid homology G with coefficients in K. And the kernel is the tensor product of the units of K times the Bauer-Strauss group, which is the K0 of L, the tensor with K. So for example, if K is Z, or K equal to Z, we get the units of K is C mod 2. So we get BFE mod 2 BFE maps to K1 of L and projects onto H1 of D. So if the Bauer-Strauss group has no two torsion, multiplication by 2 is inverted, and the Bauer-Strauss group, this is 0, and K1 is just group. So that's all I wanted to say. Thank you very much.
Thank you. Thank you very much, Willy. Questions? Let me see.
I guess I have at least one. So this, wait, can you hear me?
Yeah.
Okay, great. This pseudo-freeness assumption, is this something that has previously shown up? Like, is this
in the Exel-Pardo paper,
okay.
it is shown to be equivalent to some other groupoid, which I now don't recall, which is stronger than asking that the groupoid be out.
Okay.
So I have a previous paper on twisted Exel-Pardo, the algebra, where I try to show, to find conditions to show that the limit that the Exel-Pardo algebra be K regular. And the only condition that I mean, the smallest condition, the weakest condition that I found to guarantee this is pseudo-freeness. But perhaps I guess that this must be K regular with more generality, but I haven't been able to prove it.
Okay, and what about this condition that the complement of the unit space in the isotropy space be discrete? So is this how restrictive is this condition?
Well, I mean, not every group is not every group is satisfied. But in the paper, there is the rephrasing of this in terms of any entire groupoid arises as the groupoid of gerunds or transformation groupoid of an inverse semigroup action on the space, right? And you can phrase in terms of this action what the discreteness, what this discreteness hypothesis means. Yeah, but yeah, the point is that so essentially the result that you get for example, that you get homology the groupoid homology complex has a direct summand of the Cauchy complex is that you need to say that when you use the fact that when you have compactly supported continuous functions on a weakly Boolean space, and you restrict to a clopen, then you can restrict, you have a clopen, then you have a surjection onto split surjection onto the same ring of functions restricted to that clopen. And this is what you need, I mean, the G iso minus G0 discrete is to guarantee such kind of behavior.
Just a comment here. I think if I remember correctly, we checked this condition for Levitt path algebras.
Yeah, for Levitt path algebras.
I mean, these may not be principal, but so you have this condition.
Yeah.
Mhm.
Okay, any other question? Okay, maybe we can stop the recording.